So why do we want to do this? So one reason is to just better understand certain subtleties of the continuum. So Chern-Simons theory can be deceptively simple, and there are certain aspects that we wanted to understand from a new perspective. So in particular, the need for framing, also known as the framing anomaly, the role that monopoles play in this theory, and even something basic like level quantization. And we wanted to see directly on the lattice. So there is some literature on lattice Chern-Simons theory, which dates back to like 1989. But most of this literature sort of missed very interesting global aspects of the theory. Okay. And in terms of just more motivation, one might hope that a fully regularized definition of Chern-Simons theory could be useful in establishing exact boson-fermion dualities on the lattice. Okay, so particle vortex duality started out as an exact duality in the lattice, and one can hope to extend that to include Chern-Simons terms, and maybe give more evidence for these conjectured infrared dualities. So there is some work on this at the lattice level, but the Chern-Simons term is sort of implemented by having just massive fermions in the lattice. It would be nice to see this verified with an explicit Chern-Simons term. Okay, but it's also an interesting problem because it's not obvious that Chern-Simons theory admits a lattice regularization, and I think there is even some lore that it cannot be done. And so I'm just going to go through maybe just a few reasons, like at a first glance, why you might think that it can't be done or why it might be subtle. So one reason is that it's already in the continuum, and this is the need for framing. So if you take a Wilson loop expectation value, our correlator, where these two links, these two curves C1 and C2 are linked, then it's basically determined by this Gauss formula. All right. So, yeah, it's determined by this Gauss formula for the linking number, but we have to sum over all of these curves, and in particular, there are terms in the sum where I is equal to j, and this formula is ambiguous. Okay, so it's ill-defined, and we need to regularize it, and we do that by point splitting our curve. So we define some kind of ribbon type operator where we sort of at each point on this curve, we choose some direction, some vector, and displace by some epsilon. But depending on the details of how we do this splitting, how we do this framing, and in particular, if this sort of pushed off curve links with the original curve, then we will get a different answer for the self-linking number. Okay, but this is also like natural. It seems natural to try to resolve this on the lattice, but at the same time, it's not clear whether this can really be incorporated using a local lattice action. There's some sort of inherent non-locality. Yeah. Okay. So as I mentioned, there's a long history of people studying lattice Chern-Simons theory dating back to Froelich and Marchetti. And most of this older literature was sort of preoccupied with the existence of extra zero modes on the lattice, which had no continuum analog. Okay. And the Hamiltonian formulation, this is a serious problem. Basically, the Gaussian operator sandwiched between A and A is not invertible, so it has some extra zeros, right? And so you can't completely determine commutation relations between link variables. But at the same time, in the Hamiltonian formulation, there's a suitable choice of action where these zero modes are lifted. So it seems like it's not a problem. In the Euclidean formulation, these zero modes are sort of generic for any local gauge invariant and parity odd action. And in some sense, it has some similarities with this Nielsen-Yinomiya theorem for putting chiral fermions in the lattice. Okay. But we have a sort of different perspective compared to this older literature. There's a sense in which they sort of threw the baby out with bathwater. And these zero modes turn out to play a really important role and perform a very useful function in our construction. Okay. As I mentioned, this older literature was not really thinking about the global structure, the fact that we want a U1 gauge theory and not an R gauge theory. So in a non-compact gauge theory, there's no magnetic flux. But in a U1 gauge theory, we have a quantized magnetic flux where we can integrate dA on some closed surface sigma, and this should be integer quantized. If sigma is contractible and we find some non-zero flux, then that indicates the presence of a monopole inside of sigma. And conventional discretizations based on like Wilson formulation of U1 gauge theory always come with finite action monopoles at the lattice scale. Okay. So this is actually problematic if we're thinking about Chern-Simons theory because monopoles are not gauge invariant in Chern-Simons theory. This was known, I think, first pointed out by Rob and others in the 80s. So naively, if we try to discretize Chern-Simons theory with a U1 gauge group, these monopoles are going to cause problems for gauge invariance. But it turns out that all of these issues are either really important features of the theory or can be circumvented. So the fact that Wilson loops require framing, this is sort of built into our lattice action. Defining the lattice action requires a sort of global choice of framing. And the natural observables, actually the only observables which don't vanish in the theory, are literally ribbon operators. These extra zero modes perform this function of projecting out all Wilson lines which are not framed or which are not ribbons. And we can eliminate monopoles systematically using this recently discovered modified Balon formulation, which was discovered by Tin, Slim, and Passage and Christoph Gatchinger. It also appeared in the study of fractons by these authors.
So what about the sign problem?
Okay, yeah, there's a horrible sign problem. I don't think this will be useful for numerics at this point, but it's more just to get a really analytic understanding at the lattice level. Okay, so just some lattice preliminaries. So we work on a cubic lattice or hypercubic lattice. So we have sites, links, plaquettes, cubes, and hypercubes. And I will call fields which live on sites 0 forms, fields which live on links are 1 forms, 2 forms, etc. And D will denote the lattice exterior derivative. Okay, so just to give you an idea of how this works. So the exterior derivative of a 0 form is something which lives on links and is just given by the lattice difference. The exterior derivative of a 1 form is something which lives on a plaquette, and it's given by the signed sum of links on the boundary of the plaquette, and so on. So I'm doing Euclidean lattice gauge theory. Okay. So the Balon formulation of U1 gauge theory starts with an algebra-valued link field A, which takes values in the real line. But in addition, we have discrete plaquette fields and some P, which take values in integers. So I'll call these Balon variables. And the reason we need these Balon variables is because we want to impose 2 types of gauge redundancy. So one is the usual 0 form gauge redundancy, where we shift A by some d lambda. Lambda is just some real function on sites. But we also want to impose large gauge transformations, where we shift A by an independent multiple of 2 pi on each link. Okay. So under these large gauge transformations, the Balon field on the plaquettes shifts like a gauge field. Okay. And indeed, this Balon variable can be interpreted as just a gauge field, a dynamical gauge field for these 1 form discrete shifts. Okay, and this effectively makes this A describe a compact U1 valued gauge field. So R mod by Z is the same as U1. And just as in the continuum, we have a quantized magnetic flux. We have exactly integer quantized magnetic fluxes on the lattice. So instead of integrating dA, we sum dA on all plaquettes in some closed surface, but we use the gauge invariant, the 1 form gauge invariant combination of dA minus 2 pi n. This first term will just drop out as a total derivative. Sigma is a closed surface, and we're left with this sum of integers, which is again an integer. Okay, and then the existence of a monopole somewhere in our lattice is indicated by a cube where the field strength of this discrete plaquette field is not 0. Right, so the sort of naive first thing that we would do to construct a lattice action for Chern-Simons theory is take our A wedge dA and convert our wedge to something called the cup product and swap our integral for a sum over cubes. So this cup product is the lattice analog of the wedge product in canonical homology. Okay, so it satisfies sort of familiar properties. So the cup product of a P form and a Q form is a P plus Q form. And the cup product respects a Leibniz rule with respect to exterior differentiation. Okay, so yeah, I just want to describe what is this cup product in the case of a 1 form and a 2 form. Okay, so this is going to be some 3 form. So what we do is we start with some link on the lattice, and it's naturally associated with a dual plaquette. Okay, so it's associated with a plaquette on the dual lattice, which is pierced by L. We call that star L. And then to get a product between a link and a plaquette on the original lattice, we translate this dual plaquette by 1/2 of a lattice unit in the positive x, y, and then z directions. Okay, so that gives us this product. And then we sum over the three directions. And that's essentially that essentially up to a sign gives the cup product between a one form and a two form. Okay. So I just want to point out that these cup products break even lattice rotational invariance because we choose a particular direction to translate these dual blockades. So in principle, I could take a different convention, and this is sort of morally equivalent to a choice of framing in the continuum.
Thanks so much. Just so I understand, you could have done, for example, only plus X and everything would have worked.
No, yeah. So we have to translate it all the way up to the original lattice. So starting with the start blockade, yeah, but we could have gone like up this direction or down. Yeah, they're different choices. Okay. So it turns out that this cup product alone is not enough. We need something further called the higher cup product. Okay, so unlike the wedge product in the continuum, the cup product is not graded commutative. Okay, so I'm sort of up to signs alpha cup beta is equal to beta cup alpha plus some additional terms which involve this cup one product. Okay. And similarly, alpha cup one beta is equal to beta cup one alpha up to terms involving some cup two product and so on. Okay, so these cup I products, higher cup products, take a P form and a Q form and give you a P plus Q minus I form. Okay, so these were introduced, I think, by Steenrod in the 40s in the context of triangulations and algebraic topology, and they were only given like a very systematic combinatorial construction in the hypercubic case in this recent paper by Chen and Tata. Okay, so the way that I like to think about these higher cup products is as follows. So let's consider a line and a surface on the dual lattice. So we can have a line which pierces a surface at a point in three dimensions. This is the sort of generic point-like intersection that we can have in three dimensions. Okay, and then we do something called Poincare duality. So what we do is we set plaquettes on the original lattice equal to 1 if this line pierces the plaquette. Okay, so for example, this blue packet is pierced by this blue line. And similarly, we set all links on the lattice equal to 1 if they pierce the surface on the dual lattice and 0 everywhere else. And then this cup product is going to be non-zero precisely on the cube, which is sort of dual to this intersection point. Okay, so the cup product has to do with these sort of generic intersections. But on the lattice, unlike in the continuum, we can have sort of non-generic situations where a line hits a surface and then moves along it before moving through. Okay. And now if we do Poincare duality, it's now the cup one product, which is going to be non-zero on plaquettes, which are dual to this region here where the line goes along the surface. And similarly, we can have two lines which intersect at a point in three dimensions. That's also in a sense non-generic. And this type of configuration, again, is detected by the cup one product. And then we can keep going. We could have two lines which don't intersect, but they go along each other, and that would be detected by a cup two product. So that hopefully gives some idea of why these show up on the lattice, but they don't have continuum analogs. Okay. So here's the lattice action. This first term is just the naive thing where we replace wedge by cup, but this alone is not invariant under large gauge transformations. We need to include some terms involving the Volant variable, and then these last two terms involve dm, so they have to do with monopoles. Okay, so here I'm just showing graphically what each of these terms corresponds to. So it's like the A cup dA, we have A cup n, and you can already see from here that A cup n is not equal to n cup A. We have to include both in the action. Okay, and then, yeah, I should mention phi here is a zero form and it lives on sites of the lattice. Okay, so what about level quantization? So this is just the familiar thing. We do a large gauge transformation. We shift A by some 2 pi times an integer and shifts accordingly. And this entire action shifts by something which depends only on integer valued fields. Okay, so m and m are integer valued, but with a coefficient of k pi times I. So if we choose k to be an even integer, then the exponentiated action is invariant, and that's just the level quantization. So in principle, I don't want to say anything really about odd levels. So the odd K Chern-Simons theories are spin TQFTs, and so to get an intrinsically three-dimensional definition of these theories would require some explicit spin structure dependence. And at this stage, the cubic lattice, we don't know how to do this. So for the rest of the talk, I'll just be sticking to K even. Okay. Another nice feature of this action is that we can see the electric charge of monopoles. So let's look at these last two terms. It turns out that these two terms are actually only gauge invariant under the ordinary zero form gauge transformations if n is flat. So dn is equal to 0. What that means is that we have to eliminate monopoles in order to maintain gauge invariance of these two terms. Okay, and so in this modified Valon formulation, we just impose dn equals 0 as a constraint using a Lagrange multiplier. So that's what phi is. Phi is a Lagrange multiplier. It says dn equals 0.
Can't you say that phi shifts by lambda?
Yeah, perfect. So if we integrate out phi and we get something which is gauge invariant, then equivalently we can keep it around, but assign it some gauge transformation property. And so phi shifts the charge k under gauge transformations. Okay, but also e to the I phi is just a monopole operator. So it will just change the constraint to put dn equal to 1 on the cube and 0 everywhere else. And so this already just tells us that monopole operators have electric charge k. Okay, so it's just made completely manifest in this construction. Okay, so now let me move on to framing.
But
So
that was the conclusion. I missed the conclusion of the previous slide.
yeah, so monopole operators are e to the I phi, but phi transforms under gauge transformations. So a monopole operator has charge k. Yeah. Oh yeah, and then let me just point out. So this cup 1 term was needed in order for us to take the gauge transformation of phi to be the usual, just like Stuckelberg shift. So if we didn't include this term, phi would have to shift in a sort of non-local way on the lattice in order to preserve gauge invariance. So that's the role of the cup 1 term. Okay, so it's not obvious just by staring at the action, but it turns out that there's a sort of invariance under a peculiar type of shift of the gauge field. So if we shift A by some epsilon, and epsilon is staggered in the following way. So we choose some seed link, okay, and we shift A by epsilon, so plus epsilon, and then we shift this link, which is related by this diagonal translation. We shift that one by minus epsilon, and then plus epsilon and minus and so on through the entire lattice. That leaves the action invariant. Okay. And this is the source of the 0 modes, which were noticed in the older literature. But for us, we wanted to view this really as a symmetry and ask whether, well, first, what are the operators which are charged, and are there operators which are neutral under these staggered shifts? Okay, so let's look at a Wilson loop. That's the most obvious observable. Okay, so we insert some Wilson loop on some contour on the lattice. But then what we can do is we can choose these staggered shifts to pass through exactly one link in this curve. And we find that the Wilson loop expectation value picks up some phase, okay, epsilon. So the Wilson loop is equal to itself times a phase, which means that this expectation value is just exactly 0. And this is true for any size Wilson loop. It could be even just a single Plaquette.
Epsilon is integer or
And then some real number.
something?
Yeah, really between 0 and 2 pi, because if it's 2 pi, then this is just a large gauge transformation. But yeah, it's a real number.
And it is true even if you introduce other operators. So
any
correlation function.
Yeah, so generic correlation functions of two Wilson loops will also vanish. But yeah, that's right. Right. So this is surprising because, if a Wilson loop is charged under a one-form symmetry, a global symmetry, then you only get a selection rule, namely that the expectation value is 0 in the limit that the loop is large. So this is actually this is a gauge redundancy. This is really a gauge redundancy, which is projecting out Wilson loops of all sizes. Okay. But if we look at this picture, I think it's clear if you add a second Wilson loop, which is displaced precisely in this diagonal direction, then this is a neutral configuration. So this loop will pick up a plus I epsilon, this loop will pick up a minus I epsilon, but together this combination is neutral. So you get to your question, if you had a correlator where one of these, the second loop was like somewhere far away, but it was precisely aligned so that it picked up a minus epsilon, then that would be an invariant correlation function. But it could be rephrased as some copies of this minimal doubled Wilson loop where you translate it by one unit. Yeah. Okay, so these doubled Wilson loops are neutral and they survive this staggered symmetry. So our Chern-Simons theory also has an exact one-form symmetry. This is ZK. So we could shift A by some 2 pi over k times omega, where omega is some integer valued field, which is flat. And again, Wilson lines are the charge operators. This is true in the continuum. But if we now say that only doubled Wilson loops survive this staggered gauge symmetry, this seems weird because they would carry twice the minimal charge under one-form symmetry at long distances. Okay, so we can actually correct this by considering fractional Wilson loops, which are displaced by one lattice unit, but we make the charge 1/2. Now, a charge 1/2 Wilson loop is not properly quantized, so it's not invariant under large gauge transformations, but we can correct for that by adding a little surface which connects them. Okay, this surface is built out of the Milan variable n. Right. Okay, now at long distances, this operator has charge 1 under a one-form symmetry, and it's literally a ribbon operator. Okay, so the way that this framed ribbon operator is constructed is the following. So we actually choose a curve on the dual lattice, C tilde, and then we have two terms which produce these two Wilson loops. So this A cup delta of C tilde, this is basically just some delta function which localizes on the curve C tilde. And we take these two different orderings, which give us these slightly displaced Wilson loops. And then this surface, this strip, is provided by this term, which involves the cup 1 product of this delta function with the Milan variable. So these cup 1 products are really crucial for us to be able to construct topological, well, we'll see that they're topological, but Wilson loops with the correct minimal charge under the one-form symmetry, which are still framed. Okay, and it turns out that these framed Wilson loops are the only operators that survive the staggered gauge symmetry. So there are no other operators in this theory.
Sorry, but on the previous slides, you had the slightly displaced Wilson loops, which also survived, but they're not really framed, are they?
These are framed. I mean, here the framing is the fact that you have this, you have two copies of the Wilson loop and they're displaced by one lattice unit. The fact that you don't need a surface here because the charges are properly quantized. Okay. So for even if the charges are fractional, so at net you have an odd charge.
So you call this framed even though there's no surface.
Yeah,
that's fine.
Okay. Right. So these are the Wilson loop operators, and turns out they're topological. Okay, so the reason is that the Wilson lines are not only charged under the one-form symmetry, but they also are the charge operators for the one-form symmetry. So they generate this one-form symmetry. So a generic background field for the one-form symmetry is equivalent to inserting some collection of defect operators for the symmetry or charge operators for the symmetry. So in particular, we turn on some background field, which is related to this contour C tilde by this delta function. So we pick a curve C tilde on the dual lattice, and we set the background one-form gauge field to be equal to 1 for all plaquettes, which are pierced by this dual line. Then this corresponds to inserting a Wilson loop, a framed Wilson loop on this curve C tilde. And the fact that we can do background gauge transformations, which is to say that we actually have a genuine symmetry, is equivalent to saying that we can deform this loop in a topological way. So Wilson loops are topological.
Does that happen because of the n, because of the Milan variables on the in between? Is that what makes this correspondence possible? Or
I mean, this is just sort of a general statement. When you have a discrete symmetry, you can always view some background field.
Right. But I mean, seeing this exactly the same thing as doing that in your action, is that because of the ends? Or?
Yeah. So So when you couple, you do a minimal coupling to this one. Oops. Yeah, you do a minimal coupling to this background one form gauge field. And essentially that means you replace n by n plus 1 over k b. And when you do that, you find that you precisely get this type of term will show up. So you'll have a b couple and n.
Great, thank you.
Right. Okay. So these Wilson ribbons are topological, but they're really only topological up to the anomaly. So in reality, the under background gauge transformations where b shifts by some dv, the partition function is not invariant, but it transforms with some anomalous phase. And this means that in correlation functions of Wilson loops, we can sort of freely deform these operators, but only up to phases. Okay, so we can actually compute correlation functions with Wilson loops using this anomaly. So if we consider a configuration of background fields where this corresponds to inserting loops on C tilde prime, which have some linking, that corresponds to inserting this configuration of Wilson ribbons. And then we can use background gauge transformations to unlink these loops and like shrink them. Okay, and and in the process, because of the anomaly, we pick up a zk phase, and that's just the familiar linking relation between Wilson loops in Chern-Simons theory. Okay, so they're anons. But we can do more than you would see in a naive continuum analysis. So we can actually identify Wilson loops which have non-trivial self-linking. Okay, so here is some contour on the dual lattice, and it has this little wiggle in it, and this corresponds to inserting the following Wilson loop. Okay, and you can see that the two edges of the ribbon have some linking, and as a result, when we untwist this loop via some gauge transformation, we pick up a phase, and it's actually a Z2K phase. So it's half the linking phase. And this correctly captures what's known as the topological spin of the anon. Okay, so this just happens naturally in our lattice construction. You can just compute exactly using the anomaly, and you find this continuum topological spin. So I just want to point out this self-linking number is defined with respect to our framing choice. Right? So when we define the cup products, we chose a particular direction to sort of translate our plaquettes, and that means that this particular Wilson line has a non-trivial self-linking number, but you might draw some other curve which maybe naively looks like it's twisty in some way, but you don't find self-linking. So everything is defined with respect to a fixed framing. Okay, so I want to just talk a little bit about the connection of this 3D Chern-Simons action to a new form of the four-dimensional theta term. So yeah, this is a new form of the theta term which we proposed. So this first term here is just the naive lattice discretization of f wedge f with the cup products. And then we have a slew of other additional terms, okay, which involve the monopole in some way, Dn. So now we're in 4 dimensions, and this last term is again a Lagrange multiplier, which sets monopoles, which removes monopoles from the theory. But we can actually interpret this B, which is a one form, as a magnetic gauge field. So in these modified Boulogne formulations in 4 dimensions, the magnetic gauge field plays the role of this Lagrange multiplier. And due to the Witten effect, we can actually show that this action is only gauge invariant if we make the magnetic gauge field transform under electric gauge transformations. Okay, and the reason why we added these additional terms, okay, F1 and this term, is so that we can allow this magnetic gauge field to have just very simple, just the usual shifts under gauge transformation, okay, with the charge given by theta over 2. So this sort of improves and is slightly simpler compared to existing constructions of the theta term using this approach where the magnetic gauge field lives on the dual lattice, and to make things gauge invariant, it shifts by, it shifts by gauge transformation, electric gauge transformations, but sort of in a non-local way where you have to go to nearest neighbor sites. Okay. So another nice feature of this theta term is that not only is the action gauge invariant, but the action density is gauge invariant. So we can consider this theory on a lattice with boundary, and it's perfectly gauge invariant. Okay. And it turns out that if you set theta equal to 2 pi k, where k is even, almost all of these terms reduce to boundary terms, and they reproduce our Chern-Simons action, except for this last Lagrange multiplier, which is suppressing monopoles in the bulk. Now we can make this term localized to the boundary, provided b is exact. So if b is equal to d phi for some scalar phi, then everything localizes to the boundary, and this just reproduces our Chern-Simons action. So there's a nice interpretation of this fact that we needed to take b equal to d phi to recover Chern-Simons theory on the boundary. We could say that this is taking the deep Higgs limit of basically we're Higgsing the magnetic gauge field. And because B transforms also under electric gauge transformations, this phi is really a dionic Higgs field. And the reason we have to Higgs the magnetic gauge field is because in order to reproduce all configurations on the 3D boundary, we need to sum over all monopoles in the bulk. So it's common in the continuum to define Chern-Simons theory using some 4D auxiliary bulk. But in practice, what one does is you have some 3D field configuration, and then you get to choose some extension. First, you choose a bulk to extend, and you choose the extension, and you compute the action there. And if someone else uses a different bulk and a different extension, then you should agree up to 2 pi I. But in this context, we're working with a fixed bulk lattice, which has the topology of T2 times a disk. So we take our periodic 3D lattice and we just fill in one of the circles. And in order to reproduce all gauge field configurations on the boundary, in particular ones which have magnetic flux through some non-contractile cycle, we have to allow monopoles in the bulk. So some of those field configurations can only be extended into this topology if there's some monopole in the bulk. So to reproduce all those field configurations, we have to condense monopoles. And those monopoles are just really dions because of the Witten effect.
I'm wondering, I probably missed this, in the 2+1 case, if you put a boundary, is it still gauge invariant?
No, it's not. Yeah, that's a great question. Yeah, so that's something that we haven't really explored. It's not gauge invariant, so there should be some edge modes that you can sort of add to make it gauge invariant, but we haven't explored precisely how that works. But that's very interesting question.
What's the fate of the monopole operators? In the continuum, there aren't any monopole operators.
There aren't any monopole operators? I mean, are you saying that because they're not gauge invariant or because you don't know how to define them?
There are no local operators in the continuum.
But I think you could just try to define a monopole operator by removing a point and fixing the flux via some boundary condition. Yeah, I'm not sure. So everything we've been doing is sort of at fixed finite, finite lattice spacing. We haven't really thought too much about the continuum limit.
If you have a monopole operator and then you connect it by Wilson to another monopole operator,
yeah,
that has non-trivial correlation functions on your lattice.
Only given by the anomaly. So that's basically a trivial operator up to anomalous terms.
Doesn't matter how far the monopoles are from each other.
No, because it's a topological Wilson line. And it's basically trivial because it's charge K. So the monopole has charge K. So it's a charge K Wilson line, which should be trivial. So it's basically just a trivial operator. Up to like if you do some.
What about the endpoints? The endpoints are
Yeah, they're topological. Yeah.
the endpoints are also true.
Okay. So another nice feature of this 4D theta term is that we can provide anomaly inflow for this Hooft anomaly for this one-form symmetry in Chern-Simons theory. So if we take this theta term and we set theta to 2 pi k, where k is even, this defines some kind of SPT phase, which is protected by this one-form symmetry. What that means is that the partition function of this theory is just trivial. It's just 1 on a closed manifold in the absence of background fields. But if we turn on background fields, then this action just becomes some classical action of the background B. And it turns out that if you just take our theta term, couple it to the background field B for the one-form symmetry, the thing which appears is this Pontryagin square of B. Okay, so this is something which appears in the papers on discrete theta angles and certain discrete anomalies, and it was always hard to understand for me, but it just comes out very plainly, naturally in this lattice construction. So this Pontryagin square takes B, which is some element of, okay, it's a two form, so it's an H2 cohomology with ZK coefficients because it's ZK symmetry. And it squares it, and it gives you some element of H4 with Z2K coefficient. So the fact that this phase in this SPT is 2 pi I over 2K is telling us that this is some operation which takes our ZK 2 cocycle and maps it to some Z2K 4 cycle. And then we can sum that over our lattice. Okay, so this is a well-defined operation in cohomology. So on a closed manifold, this thing is gauge invariant. But if we put it on a manifold with boundary, it's no longer gauge invariant, but it provides anomaly inflow for the 3D Chern-Simons theory.
Alright, so what is B in connection to the previous definition of the theta term, where it wasn't before?
So I haven't coupled in this definition. I haven't coupled. Sorry, it has no relation to little b. So capital B is the background field for the one form symmetry.
Got it, okay. So you just, got it.
So we have anomaly inflow exactly on the lines. Okay. Good. So I guess I'm a little bit early, but I'll just summarize. So what did we do? We wanted to discretize Chern-Simons theory in a way where we could capture as much of the global aspects as possible. And in order to do that, we use this new modified Balon formulation. Okay, so we were able to demonstrate gauge invariance under small and large gauge transformations. That gives us level quantization. We have explicit monopole operators which carry electric charge. We have a one form symmetry, and it's a Hooft anomaly. Wilson loops are framed. You know, the natural observables, the only observables in this lattice theory are these ribbon operators. They're exactly topological up to the Hooft anomaly. And as a bonus, we get this new form of lattice theta term, which provides anomaly inflow. Okay, so I think that we did some of the most, basic things, constructing the action, verifying all the symmetries and things like this, but there are many worthwhile generalizations and applications. So one is repeating this in a canonical approach. So I mentioned this paper by Eliezer and Semenoff. So they construct a canonical formulation of Chern-Simons theory, really with R gauge group, okay, non-compact, but they do it in such a way that there are no extra zero modes on the lattice. So that's a natural starting point. And the goal would be to just incorporate these Balon variables to make manifest large gauge invariance. Okay, so we could do that both for the Chern-Simons term, but also for the theta term. I've sort of mentioned the odd K theory. This is a spin TQFT, so it would require some spin structure dependence. It's possible that this could be also defined using some auxiliary bulk, but I'm not sure. I'm not sure about the details. So one might have to pass to a triangulation rather than a hypercubic setup. As far as generalizations, I think something which is obvious is just generalizing this theta term to axion Maxwell theory. So there you have some compact scalar chi, and we want a formulation which sort of manifestly preserves its 2 pi periodicity. And it's possible that this Chern-Simons construction would also help us understand or have a lattice construction of these new non-invertible defects which appear in the axial symmetries of these axion Maxwell theories and other theories in 4 dimensions. As Sri pointed out, it'd be interesting to look at what are the edge modes on this for this theory on a lattice with boundary, try to make some connection to the continuum story with the chiral boson. And then finally, something which we have not fully understood is the role that the gravitational anomaly plays on the lattice. So this need for framing in the continuum is really just a symptom of the gravitational anomaly, where the partition function is not quite invariant under a change of framing. It's hard to see exactly how this gravitational anomaly would be reproduced on a lattice, because it's just, you're working on a torus, it's just some fixed geometry. But maybe by comparing partition functions with different choices of these cut products, we could try to make some connection there. But we'll do that for future work. Okay, so that's all I wanted to say. Thanks.
Yeah.
So I was just wondering, the 2+1 case, let's say, if I wanted to understand the Minkowski formulation. Well, what are are there similar challenges to the Euclidean
You mean in the continuum or in the, on the line?
on the line?
So I guess I would, by Minkowski, you mean like Hamiltonian formulation?
Yeah.
Yeah.
So, for example, there was a comment, right? There's a bad sign problem.
Oh, sure.
So is the
Yeah, yeah,
does it
okay.
survive in
Okay, that's great. Yeah, so the Hamiltonian, if you set this up with the Hamiltonian vanishes. So you just have like some set of commutation relations which need to be satisfied. So I guess in that sense, there's no sign problem because there's no Hamiltonian. The Hamiltonian is 0. Yeah.
It's not useful.
I mean, it might be useful. It might be useful for something. Yeah, actually, in that, I hadn't thought about that, but that might be a way to get around the sign problem because the Hamiltonian just vanishes.
You haven't mentioned periodic boundary conditions.
Oh, okay, good. Yeah, I took periodic boundary conditions.
Like
everything is periodic.
checking the okay ground states.
Right. Okay. Yeah. Yeah. We haven't done a systematic. We haven't computed the partition function. We haven't looked at expectation values of non-contractible Wilson loops, things like this. So yeah, I don't know. It requires some work, and I think probably these 0 modes might make that technically a little bit challenging. But
Which 0 modes?
these sort of non-local staggered 0 modes. I'm not sure. We haven't tried.
And the non-abelian.
Good. Yeah. So the Valon formulation does not have an obvious non-abelian generalization. The closest thing is like a heat kernel action, but that's sort of like a Poisson dual in some sense of this Valon formulation. So I don't have any immediate things to say there. Christoph Gatchinger has this approach called abelian color cycles, where you take your Wilson action for like SU2 gauge theory and you write the plaquette term as like an abelian product through some space which takes into account the non-abelian structure. So maybe that would be helpful, but I don't know.
Yeah, so I wonder, so at the beginning of the talk, you mentioned several other tools. So for example, regularize the Chern-Simons term as a massive format come to gauge field, right?
Yeah.
That seems to be a more convenient way of doing that. So
Convenient and
for
like
example, we don't have to define so many things on their links and their plaquette and
right.
it's actually, well, I mean, so another perspective might be that, for example, if I want to do like the lattice representation of SU2 Chern-Simons theory, then they say a AAA term, which I imagine would be kind of awkward to put on lattice, but actually if I just use a massive format, it seems to be easier. So I wonder,
Right.
so this approach has some advantage over that, or?
So okay, that's a good question. I guess certainly in the continuum, if you integrate out some massive fermions, then you generate Chern-Simons terms, but I don't know that that's been explicitly verified on the lattice. I mean, I don't know how that would be right. I mean, you could say that that's just your definition of the Chern-Simons theory is the result you get from integrating out fermions. But this is a way of just directly formulating the Chern-Simons theory itself.
So, I mean, a challenge for that would be on the previous slide, there was a list of things that the lattice definition should satisfy if you're really getting Chern-Simons, framing, Hooft anomalies, all this. And I don't think it's so easy to show this on the lattice fermions. Yeah. So I'll take advantage of.
But it might be the case that in applications,
Yeah.
using massive fermions is just simpler and maybe gets you everything you need. But we were really looking for a just intrinsic definition of Chern-Simons theory on the lattice.
Did you ever, you want to understand the theory, how to formulate it on a lattice. But if you would, what is the smallest possible lattice where this still all works? Because there's only a 4 to the 3 lattice, you actually might be able to simulate it.
Oh, I see. Despite the sign problem, just because it's so small.
4 to the 3,
Right.
you might be able to do it because you could take zillions of
I see. Yeah, okay, that's very interesting. Yeah, so I'd say a 2 by 2 by 2 is the smallest that you, or the smallest. That you do.
Okay, the generate states, right?
Yeah, that's right. But so it's important for the staggered symmetry, you need an even number of sides in each direction. So by 2 by 2, I think would be the.
Is this generalized to 5D? Can you do 5D Chern-Simons theory?
Yeah, presumably, yeah. Yeah, so this paper by Chen and Tata, they give a combinatorial definition of all of the cup and higher cup products and arbitrary dimensions for arbitrary quantities. So it's just a matter of deciphering their formulas and translating it into a simple, I don't know. I mean, we gave in the paper, we give very explicit definitions of these higher cup products, which previously in the literature, they're very opaque. So hopefully it's some service to the community, but yeah, I think it should work fine.
And might that shed any light on some new lattice definitions of fermions? So we put an edge mode and now we're stuck on the edge, which is more or less some kind of.
Right, yeah, maybe. Yeah, I think first we'd want to look at the edge modes and the 3D case, but yeah, that's interesting.
Are there any other questions? Yes.
You do non-abelian Chern-Simons theory.
I not in this approach in any obvious way. Yeah.
What is the
So I mean, the sort of starting point here is that you work with algebra valued fields. So you could work with some algebra valued fields, but then I think it gets very complicated with the the regions of integration are very complicated in the R measure, for example. But I'm not sure. Maybe it can be done. So yeah, maybe you have some comments. So you have this, constructions of these semi-abelian gauge theories in Milan formulation. So that's sort of the closest thing.
If the algebra itself is abelian, that kind of thing. It goes beyond that kind of stuff. So one thing you can do is, for instance, you could easily cook up a general K-matrix.
Yeah.
So once you have a U1 with K-matrix gauging some topological tools, you can get very interesting non-abelian theories.
I see.
Just from to gauge theory gauging the influality, topological surface, you can get.
I see. Yeah.
So, Alex, you earlier mentioned that you had some insights about the Chern-Simons formulation and how that compares with Maxwell Chern-Simons.
Yeah.
I
So.
think that might also address the question.
That's right. Yeah. So the zero modes get lifted by a Maxwell term. So that means you have just ordinary Wilson loops in that theory as well. And one expects that if you compute some correlation function of ordinary Wilson loops in Maxwell Chern-Simons, that at long distances, those reduce to these long distance correlation functions with these ribbon operators in pure Chern-Simons theory. But with the ordinary Wilson loops, you will not be able to see. So you'll reproduce the correlation functions of untwisted ribbons in the pure Chern-Simons theory. But at the same time, that theory still has, Maxwell Chern-Simons theory still has this exact one-form symmetry. And so it's now the Kukov-Witten operators, which are topological and generate that symmetry, are ribbons.